All right, let's go ahead and get started. I'm going to go ahead and get the sign-in sheet passed around. All right, so a couple things. I see you all made it back and the storm didn't take us all to Emerald City of Oz or anything. Okay, 1, 2, 3, 4. Okay, let me go ahead and give you this. This is the truss analysis example that we did last time. And we'll just sort of like briefly go through it again because I want to go through the appropriate steps in Excel today. We might get the whole thing done. I don't know. We'll see. Hopefully by now with our in-class exercise with the bar analysis problem and the homework assignment that you all did, you should be a little more comfortable with what we're going to do in Excel. So some of the rote stuff should go rather quickly, okay? Now before we go back through this example, I do want to bring this up. This is a summary procedure sheet that I'm giving you all. Let me get it in page view so we can actually kind of see the thing. Okay. All right, so let me go ahead and pass this out, and then we will discuss this. There's that. There's that. There's that. There's that. There's that. Did I give you an extra? Oh, whoops. And then give you this. Okay, so I want to, like, I guess, how do I want to put this? I want to really emphasize to you all that what is on this sheet is really no different in any significant way from the bar analysis procedure. It's really not that much different. The only difference is the introduction of this beta matrix and the fact that we have to rotate a system from a local coordinate system to a global coordinate system. So let's walk through this, okay? So we say, all right, let's develop local element stiffness matrices for each element. We will then develop a rotation matrix for each element. We take that local stiffness matrix, we convert it into global, and then we assemble. Now, with bars, we didn't have to deal with the beta matrix or going from local to global, but in the process, you know, in large was the same. Develop a stiffness matrix for each element, assemble it into a stiffness matrix for the whole thing, right? Then we say, all right, we're going to develop a load vector for the whole thing, right? Apply our boundary conditions, and then once we get our boundary conditions, we solve for a global displacement vector. Now I'm calling the global displacement vector U on this one because I want to differentiate the difference between local displacements and global displacements. Speaking of, once you get a displacement vector for the whole thing, you form a displacement vector for each individual element, right? Now, keep in mind that's going to be in global coordinates, so we must then rotate that back into local coordinates by multiplying by beta. And then now that we have local displacements, we already got local stiffness matrices, the KE primes. Take KE primes, local stiffness, local displacement, local force vector. And this P vector is going to tell us how much axial force is in each truss member, right? So this will give us the, step 7 will give us the displacements for the whole truss. Step 10 will give us the axial forces in each member of that truss. And then if we want to look at steps 11, we can just take the whole stiffness matrix for the whole thing, the displacement vector for the whole thing, get the force vector for the whole thing, and the values that we didn't know before, those are the support reactions. So when you think about a truss analysis, what do you care about? You care about your support reactions, you care about the forces inside each member, which if you want to calculate stresses inside each member, just take them and divide it by the area. There's not real, they're not what I call primary results. They're more secondary results, things like stresses. Same thing with strains. You can calculate the displacements for each member and just take the displacement, divide it by the original length. Remember, change in length divided by original length will give you strains. So forces, displacements, and support reactions, that's what we care about when we do a truss analysis, and this procedure will give us all of that, right? So everybody okay with that? Let's real quickly, okay, everybody sign in? All right, let's real quickly go through the the example together, make sure that we're clear on that. Did everybody get a copy of the truss analysis example handout? And everybody got a copy of the truss analysis procedures? Okay. All right. Let's real quickly go through this again, make sure that we're clear on what's going on because we're going to repeat a lot of this together today. So if you haven't opened Excel, go ahead and do that because we might do the whole example, we might not. I just want to play it by ear and see where you all are at. The last thing that I want to do is leave you all ill-equipped for your at-home celebration, which I will be giving you all a homework assignment. You all haven't had me for class, so you probably don't know that I don't refer to them as exams. I refer to them as celebrations of learning. So some of you had me for class, and you're familiar with that terminology. So just heads up. All right. Okay. So last time we looked at this example, we were looking at a 2-bar truss. The E value was the same across the board. We have different areas for each member, so that resulted in ultimately different AE values, different stiffnesses, axial stiffness. Let's do a pop quiz, make sure we understand what's going on. How big is the whole system stiffness matrix for this problem going to be? It's not 3 by 3 because we don't have one displacement on each joint anymore. We're dealing with a truss. We have two, so it's 6 by 6. Okay, so the whole system is going to have a 6 by 6 stiffness matrix. Each member is going to have a 4 by 4. There we go, because each member, 2 joints, 2 displacements, 4 by 4. So we have 2 4 by 4 matrices that we must assemble in order to achieve a 6 by 6. Make sense? Okay. Now here's our analytical model. This is just sort of our legend, if you will, for how we're going to do the problem. I'm saying this is degree of freedom 1, this is degree of freedom 2, this is degree of freedom 3, 4, 5, and 6. Everybody okay with that? Just to give you a little bit of a preview of shape of things to come, I'm going to pull this up. This is your at-home celebration that's coming on. It's not going to be 2 problems, it's just a single problem. Okay? Now for this truss that I'll show you, you're going to determine the displacements at the joints, the forces in the truss members, and the support reactions. Here's the truss. Now notice what I've given you is the truss itself, but then over here I'm giving you the member codes so that everybody assembles it and does the problem the same way. Okay? So that we've all agreed that for this joint, the horizontal displacement, that is degree of freedom 1. For this joint, the horizontal displacement is degree of freedom 7. Everybody, so that way we're all agreeing on the same thing. Okay? So for this truss, we have 5 members that we must assemble. Each of them have a 4 by 4 stiffness matrix. We must assemble each of those 5 members to achieve an 8 by 8 for the whole system. Right? Everybody okay with that? All right. Okay. So, now a couple other points I want to make for this problem, okay, and I'll go ahead and do this now. When we did our row elimination and column elimination, if you recall, we eliminated rows 1, 2, 5, and 6. Columns 1, 2, 5, and 6. Remember when we did that? Okay. The reason why, keep in mind, 1, 2, 5, and 6, we did that because both of these are pinned connections. Okay? So I'm not going to tell you the answer, but I'm more or less going to pose the question to you, and you all can come up with the answer on your own. But see, here we have a hinged connection. Here we have a hinge support. Here we have a roller support. So we have 1 and 2 associated with this one, and this one we have 5 and 6. Do we eliminate 1, 2, 5, and 6, or is that the case? And if not, which ones do we eliminate? I'll let you all figure that one out. Everybody good? I think some of you have kind of already figured it out on your own. So, everybody okay? All right. Now, going back to the example, just making sure the procedure is fairly rote at this point, we take each element one at a time. Remember, we know the area and the modulus of elasticity. The length, if it's a horizontal or a vertical member, you should be able to just look at it and see what the length is. If not, Pythagorean theorem will give you the length. So you can calculate AE over L pretty easily. And then remember, when you're doing your sines and cosines, remember the key. You always go from a higher numbered node to a lower numbered node, okay, to keep consistent with your sign convention. So our cosines and sines were 1s. So for this first element, there was actually no difference between the local stiffness matrix and the global stiffness matrix because the member was horizontal. It was flat, okay? That was for this member. This one, for element number 2, not necessarily the case, okay? Because that member was angled. Because of that, there is a difference between local coordinates and global coordinates. So we went from, keep in mind, again, we go from higher to lower, okay? So going from higher to lower, we got negative values for change in x and change in y, okay? Everybody all right with that? So we got negative sines and cosines because how do you calculate the cosine? Change in x over L, change in y over L. And the length of the member is always positive, okay? Everybody all right with this? Remember, length is just Pythagorean theorem. Everybody good? So, local stiffness matrix, beta transpose K beta gives us that. And we'll go through that today in Excel. All right? We take this matrix, again, keep in mind your member codes, okay? They're not just thrown on there. Those numbers correspond to the degrees of freedom for that element, okay? If we're looking at a different element, those numbers would change. Everybody good? Assemble them accordingly to obtain the stiffness matrix for the whole thing. Apply boundary conditions. We are crossing out 1, 2, 5, and 6. 1, 2, 5, and 6, okay? Because those were the ones associated with the supports. If the support conditions were different, you would strike out different rows. You would strike out different columns, okay? Maybe later on we'll talk about, well, what if you don't necessarily strike them out? What if instead of the displacement being 0, what if you had a defined displacement? Which is probably more of a civil engineering type problem for those of you who have any experience with civil engineering or geotechnical engineering. There's this whole thing called support settlements that we kind of have to deal with. So what happens if you're analyzing a structure and you know that support settled 1 inch? It's not the displacement is 0, it's that the displacement is 1 inch. So that's another story for another day. Long and short of it is we take our stiffness matrix, we reduce it to obtain a reduced stiffness matrix based on the boundary conditions for the structure. We can write a force vector. Why is that negative 10? Load's going down, right? Remember that? We have a downward force, down's negative. Plug and chug. So let's keep this in mind. What do these displacements mean? This U3 is a positive 0.08. That means I have positive 0.08 inches of deflection or 0.08 inches to the right, okay, because this 3 is a horizontal displacement. This negative would be 0.28 going down, which makes sense. I mean, this number better come out to be negative. I mean, the only thing we're doing to the truss is taking it and yanking it down. It better just deflect downwards. That's kind of how physics works. So that number, the fact that that number came out in the sign that it should be a little bit of a gut check that what you're getting is the correct answer. Make sense? Okay. Take those displacement vectors, split them apart into global displacement vectors for the whole thing. So this is U1, the global displacement vector for member number 1. For member number 2. If you had 7 members in the truss, you'd have 7 of these. If you had 956 members in the truss, you'd have 956 of them. Take each one of them, rotate them to get local displacements, okay? Displacements along the member, okay? So you just beta times that, okay? Local displacement vector for the whole thing. We already determined local stiffness matrices. Keep in mind, again, local displacement matrix. Plug and chug, and you'll get a local force vector. Again, when you look at a local force vector, what should you see when we're looking at trusses? You should only see 2 values. They better be equal magnitude, opposite directions, okay? So negative, positive, bam, bam, positive, negative, bam, bam, right? So we can summarize our answers pretty easily. A trick is to just look at the third number. If it's positive, it's in tension. If it's negative, it's in compression. That's just a little trick. Okay? We can also develop, we have our stiffness matrix for the whole thing. We have our displacement vector for the whole thing. Calculate a force vector for the whole thing. The values that are highlighted are the ones that we didn't know before, and those just happen to be the support reactions. So there's a nice, neat little summary of the whole problem. Any questions? Everybody good? Okay, so let's do some of this problem together. We might not do the whole thing. We might. It just depends on how things go. There are a few things I really want to get across and make sure that everybody's clear on. So let me do this. Let me find a nice little picture of the truss in my slideshow. There we go. That's a good one. Just so I have something to look at over here. Okay. The first thing that I'm going to do right off the bat is I'm going to make myself a little table. I'm going to say joint. I'm going to say x coordinate and y coordinate. Maybe what I should do is, since I'm trying to get more into a finite element set of terminology, I should call that a node. Now, how many nodes do we have in this structure? 3, right? 1, 2, and 3. Okay? Well, we'll center that up a little bit, make it kind of neat. Okay. So let's keep this pretty straightforward. Okay, so here's my coordinate system. Does everybody see how I've got my y-axis and my x-axis indicated as such? Here, I'll make this a little bigger. We can all kind of see what's going on. Okay. All right, let's start off with a simple one. What are the coordinates of node number 3? 0, 0. Right? Okay. Now, what are the coordinates then of node number 1? 0, 60. We got to maintain a consistent unit system. And again, that's the same thing if you're dealing in SI or not, because it's real, attempting to express member lengths in meters. And then if you have an E value and it's in gigapascals, the appropriate length unit is probably millimeters. So you'd have a disconnect right off the bat. So make sure you're using consistent units with whatever you use. Okay? Now, so what are the coordinates of node number 2? And 60, right? Oh, 60. Sounds good, right? Let me make this a little smaller so I can work with this. All right. Simple, right? Pretty straightforward? Okay, now, let's do a little bit of calculation here on the side, and we'll see if we can come up with a consistent way of doing it. All right, so an element. How many elements do we have in this problem? 2. We're talking about how many bars in the truss. Well, I got 2 bars. Okay. All right. Now, let's start off with A. What's the area of these elements? One for the first one and 2 for the second one, right? Is that what I got? Okay. What do I have as the E value for each element? 29,000, right? Made out of steel. Bless you. Okay, now, before we start calculating member lengths, let's do this. Let's, and you all can just call it dx if you want. I'm going to actually go to insert symbol and put in a delta. Delta x inches, and then delta y. You all can call it whatever you want. If you want to call it dx, dy, it doesn't really matter. Okay. All right. Let's go back to our discussion. How do we calculate these change in lengths? We go from the higher number joint minus the lower number joint. Higher number node minus the lower number node. So let's look at element number 1. We're looking at this one right here. What are its respective nodes for this one? 1 and 2, right? So to calculate delta x, watch what I'm going to do. Watch this. Okay? I'm going to go here. I'm going to say equals the x coordinate here minus the x coordinate there. Higher minus lower. Okay? Everybody see that? All right? What about the y coordinate? Well, I should just be able to drag that over. Again, higher minus lower. Does everybody see that? Okay. So what do I do then? Somebody tell me. If I want to calculate delta x for this member, what do I do? Is it 120 minus 0? Now think about it. If I want to calculate this value, higher minus the lower, I take this one minus that one. Higher number joint minus lower number joint equals x3 minus x2. Higher minus lower, okay? Does everybody see that? Is everybody okay with that? Everybody got this right here? Okay. So now what I'm going to do is calculate the length. Okay? How do I calculate the length using delta x and delta y? If I have a triangle and I know how the measurement of this leg and this leg, how do I calculate the length of the hypotenuse? Pythagorean theorem. There you go. So watch what I'm going to do. I'm going to say equals square root of this squared plus this squared. Simple, right? It's just Pythagorean theorem. Everybody all right with this? So I get 120 for this one, copy and paste, and I get 134. Do these numbers reflect what's really going on? Yeah, I mean, element number 1 is 10 feet long, or 120 inches. Element number 2, you can see, is going to be a little bit longer. It's about 134.16 inches. Everybody okay? Any questions? Yes? Yeah. Then, well, I mean, you tell me. What do I calculate? Go ahead. I mean, so take that and then square it plus that. I mean, right? Then you got to close it. There you go. All right, it's just Pythagorean theorem. So, everybody good? Okay. Now, you all tell me, okay, I've got the length of each member, right? How do I calculate the cosine, and I'll just say cosine and sine. Now my OCD is kicking in. I got to put the little theta in there. Symbol, where's that? Cosine, and that. You tell me, how am I going to calculate the cosine and the sine using this data? Let's start off with the cosine. How do I calculate the cosine? Well, cosine is going to be adjacent. But remember our formula. It should be right there. So tell me what to do. I mean, keep in mind, hopefully my little pen will work. Let's see if this works. We have a member, right? This is delta y, this is delta x, this is our angle that we're looking at, and this is L. How do I calculate the cosine of that angle? Delta y by L? delta, I mean, this is delta y right here. There we go. Delta x by L, right? Cosine adjacent over hypotenuse. Bam, over that, right? So watch what I do. Okay. Let me go my arrow. We say equals delta x divided by L. Right? That'll be the same down here. I mean, look what it's calculating. Delta x divided by L, right? So tell me, what do I put here for this one? Delta, there we go. Delta y divided by L. Look what we're getting. We're getting 1 and 0 respectively for the sine and cosine of the first member, indicating that that member goes along with that coordinate system, which it does. It's horizontal and in that direction. Second member, not so much. Everybody okay with this? All right. Since we need this value, I'm going to go ahead and calculate AE over L for each member because we're going to need that for the stiffness matrix. So equals A times E divided by L. How are we feeling? Not too bad, right? Pretty straightforward? What's up? Okay, what particular point? Hold on. Help me out. You just, here, okay, you can just go to copy right here, see it? And then paste. But the problem is, okay, you've got to manually go through and say x3 minus x2, and then y3 minus y2. But, okay, well, I don't know what's going on here because that needs to be over there. I don't know what's going on there. All right, are you good for now?
Yes.
Okay, all right. Y'all good? All right, we can take them and make sure everybody, I want to make sure everybody's on the same page. Okay. What's going on? What's that? You're good? Oh, well, okay. Well, we're just going through this example right here. Hold on. Give me one moment. This is what we're working off. Okay. Oh, well, you got to start off, hold on. You got to start off with equals. There you go. And then parentheses, and then it's just that squared, like I'm just going off that one right there, plus that squared. See what I did? Just that right there. Right here. Just shift right there. You good? Okay. Y'all good? Good. Okay, you're good. You're good. Y'all good? You good? Okay. You don't, okay, when you're doing, all right, one point to make, when you're doing cell by cell calculations, you don't need to do Control Shift Enter. You can just, if it's just cell by cell, you don't need to do the Control Shift Enter. Okay, so cosine just equals that divided by that. Okay, whoa. Okay, Okay, you've got this value referring over here, like you put L4, and I'm not sure why. That needs to be like equals square root of that squared plus that squared. Like you had it like clicked all the way over here. I don't know why. You good? Everybody good? Okay. If it's all right, I'm going to erase this little diagram I've got here because I need room on the sheet to actually do some work. Okay. Now, the big thing with this type of analysis, I'm zooming out a little bit so I can see what's going on here. Okay, the big thing with this type of analysis is making sure that you're organized, okay? Because as soon as you start getting sloppy with your work, you start to get lost where you're at. So if it takes time for you to make your sheet nice and neat and organized, take that time because ultimately you'll spend less time on the problem. So I'm going to work with element number 1 right now. Work with element number 1, okay? So let me ask you this. How big is the stiffness matrix for this member going to be? 4 by 4. Okay, so here's what I'm going to do. I'm going to say, 1, 2, 3, 4, 1, 2, 3, 4. I'm going to box that up. And we'll say this is K1. But watch this. K1 prime, okay? There is an important distinction behind that. Now, you all have the sheets in front of you. Tell me, let me ask it to you in this fashion. Most of the values in K1 prime are what? Most of the entries in this matrix are going to be what? Like what does the local stiffness matrix for a truss member look like? Local stiffness matrix. There we go, 0. Most of them are zeros. The only ones that aren't are, like here, I'll sort of highlight them in. The only ones that aren't 0 are like these. Everything else is 0, right? Everybody see that in your notes? Okay. So what I'm going to do is I'm just going to go ahead and fill the whole thing in with zeros. Whoop. And then maybe center that up a little bit. Make it neat. Okay. Now it's this one, this one, this one, and this one that are different. These two values here are what? AE over L. Is it positive or negative? These two. Positive. These two are, there we go. Have we already calculated AE over L for this element? Yeah, it's right here, right? So what I'm going to do is I'm just going to say equals that. Equals negative that. Equals negative that. Equals that. Okay. Now I'm going to take a little bit of time and format this a little bit. Let's see. Give it some color so I can recognize what's going on. Maybe make this a little bit lighter. Something about like that. Now, help me out. Member number 1. What are my codes going to be associated with this element? One, 2, 3, and 4, right? Now, how am I getting that? Again, I'm going off of this. Remember, we are looking at that first bar. We're looking at this right here, at that, right there. And that element is connected to 1, 2, 3, and 4. So what I'm going to do is I'm going to say 1, 2, 3, and 4, 1, 2, 3, and 4. And let me center that up. Clean that up a little bit. Everybody okay with this? What's that? Okay, if we go back to, that's a good question. Let me go back here a little bit. Okay, so the question was, why are the values only associated with 1 and 3? If you recall, this is what a stiffness matrix looks like for a one-dimensional bar element. The only difference between a 1D bar element and a 2D bar element is the introduction of more degrees of freedom, but the mechanics are the same. So a 2 degree of freedom bar element just has a 2D bar element just has 2 degrees of freedom at each node. But just because I've added more degrees of freedom doesn't mean that that element can't resist load in more ways if I'm still assuming the same behavior. So because of that, this element only has stiffness associated with its axial behavior. In other words, 1 and 3. So locally, the stiffness matrix looks like this. I'm not saying that's what it looks like globally. I'm saying locally, that's what it looks like. So that's why there's only values associated with 1 and 3. That's a good question. Does that help out? Okay, good. All right. Okay. Everybody good? Now, what else am I going to need for this element? I mean, you've got a step-by-step procedure, right? So what am I going to need for this? Well, I'm talking about for this element, what are we going to need? A rotation. We're going to need beta, right? So you're talking about the difference between local and global. So we're going to need a beta matrix. So, because I'm lazy when it comes to formatting, I'm just going to copy this over here, delete all its values. I don't know, make that orange. Make that orange. Insert symbol. You don't, I mean, I'm sitting here getting, sort of fancy with the, my formatting and whatnot. You don't need to be as, verbose as this. As long as it's neat and organized, you can do whatever you want. Okay. Now, what does the beta matrix look like? Let's pop quiz you again. Okay. Let's just see if you're paying attention. These values right here, 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 and here, what are they? In this upper right quadrant, what are they? 0. And then down here, there, 0. Okay, there we go. Okay. Now, where are we getting that, just so everybody's clear? We're getting that from this definition right here, aren't we? This is our beta matrix. This is what we're after. So maybe what I will do is put this, I don't want to move that there, put that here for reference. Just copy and paste the image so that we can all see what we're looking at. Okay, across the main diagonal, what do I have? Cosine. So I've calculated the cosine for element number 1. What is it? 1. So just so I'm referencing that cell, although it's a formality for this member, but I'll just say equals that, equals that, equals that, equals that. Everybody good? It's a formality for this problem because you could just go ahead and type it in, but I just want you to be familiar with this. Okay, so this term right here, the second column, first row, that is a positive sign. But this is negative sign. Positive sign, negative sign. So we'll say equals the sign. Whoop. Equals negative sign. Equals negative sign. Equals sign. Now, it just so happened that this particular member had 1s along the main diagonal and 0s everywhere else. Hence, we're dealing with an identity matrix. Very possible that we could deal with something different. Very possible. I'll give you all a minute because I want you all to catch up. good. Looking good. All right, looking good, looking good, looking good. All right, looking good. Looking good. Are you still working on it? Yes, sir. What's that? Oh, you want the symbol. Oh, I went to insert and then symbol over here. And there's like a whole like library of stuff that you can enter. And I mean, like if you scroll up a little bit like here, like there's the Greek alphabet and there's beta. You don't have to do that if you don't want to. That's just, you know, being a little fancy with it. But if you want, that's fine. Okay, looking good, looking good, looking good. All right, everybody good? Now, let's make sure that we're following what we need to do. We've got a local stiffness matrix and we have a rotation matrix. What do we need to do with them? We need to get a global stiffness matrix. How do we do that? There we go. We have beta transpose times K prime times beta. Okay, watch this. Okay, so here's what I'm going to do. I'm going to like create another little series of cells over here. We'll call it K1, but we'll take off the little prime symbol because it's global. And I'll delete everything in here. Maybe make it another color so I know what I'm doing. Maybe make it yellow. Okay. I'll give you all a second to get everything ready. I just like using the different colors so that I'm, you know, so it's kind of clear what region I'm working on. Excuse me. I haven't typed anything in yet because I want to walk you through this. Now, that means, keep in mind, we have to multiply 3 matrices, right? Now, when you all are ready, I want everybody to watch what I'm doing, and then I'll have you all do this. But y'all need to watch what's going on up here. Now, you should have already done this on the first homework assignment, so you should have done something very similar, okay? Everybody watching me up here? Okay, so watch what I'm going to do, okay? When you use matrix multiplication commands in Excel, they only work for 2 matrices. You can't do 3 of them. So you have to do what's called a nested matrix multiplication. So watch what I'm going to do. It's beta transpose K beta, right? So let's deal with the first one. Beta transpose and K, or K prime. Beta transpose and K prime. So watch what I'm going to do. Equals, keep in mind I've got the whole thing highlighted. Y'all watch me while I'm doing this because you know, I want you to watch and then do it. Okay, so keep the whole thing highlighted, equals M mult of what? The first one's beta transpose, right? So we'll say transpose of beta, close that, and then K prime, okay? So close that. Okay, so does everybody see what I've got up here? Okay, now that is a matrix. I need to take that matrix and multiply it times that, right? Beta transpose times K times beta. So watch what I'm going to do. Watch the formula bar. I'm going to say this whole answer, let's matrix multiply that whole thing by beta. So see how I'm doing that? I've got to use 2 matrix multiplication commands. Now, Control, Shift, Enter. I'm going to leave that up there so that you all can see what it looks like. Leave you all to that. Now, if you want, you can set up extra cells in your sheet to do, you know, the first 2, and then take that answer and multiply it by the third one. That's fine, you know. It's however you want to do it. You know, if you only have to do this once, though, I don't see the reason in doing it like 3 different times, or just do it, you know, formulate your cell once, and then, as you'll see here in a little bit, we can copy and paste the whole thing. Now, a check for this particular problem is that when you're done, you should get the same thing you started with, that this is K1 prime, this is K1, they should be the same. For this particular element, the element is oriented like this. I'll give you all a little bit. Let's see. Yes, sir. Because, okay. All right. Let me go back to this right here. Here's my truss element, okay? What I'm doing when I formulate that element is I'm assuming it only responds this way. So mechanics tells me that this is what the stiffness matrix looks like. But if I look at it from a, 2 degrees of freedom per joint, like here's what I'm saying. If I take this joint and I move it up, well, no, I physically grab it with my hands and move it up. It did not take any force to do that. I'm saying it only takes force to take this joint and move it like that because I have to stretch the bar. Do you see what I mean? But to do this, it doesn't take any force at all. So that's why like that particular value is 0. And I'm saying that all the associated values are 0 when it comes to moving that joint this way. Only that way that I actually have to overcome something. And that's because I'm dealing with trusses. If it was beams, it'd be a different story. Yes, yes. Do you have a question? No. Oh. How are we doing? Doing good? Oh, yeah, okay. So if you go, you're at the right spot. If you go here, there's like, all different types, and you can scroll up. Then there's Greek, and then you can see there's all the capital ones, and there's all the lowercase. That's if you want to get fancy, though. You don't have to. If you don't want to, you're not going to hurt my feelings. Now everybody's doing it. Like I'll say this, when we look at beam elements for that 1 and 3 issue, beam elements, it's not the case. The entire stiffness matrix is populated with values because with beams, you're bending it. And we're not considering bending for this. All right. Everybody good? Okay, now, let me hit escape. I'm going to zoom out a little bit because I want to ask you this question again in regards to the whole system. How big is the stiffness matrix for the whole thing? 6 by 6. So I'm going to set myself out a little region over here. And you all can format it however you'd like. Let's see. I think I did that right. 6 by 6. Yep. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Make it another color just so I know I'm going from step A to step B. Okay. Now what I'm going to call this, I'm going to call this capital K1, just so I know what I'm looking at. So for this element, where do those terms populate the whole stiffness matrix? This is assembly now. So I'm taking this local stiffness matrix. I'm trying to figure out where does this element level stiffness matrix fit into the whole system? Goes right up here, doesn't it? Why does it go there? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. See what I mean? So I propose that for the whole system, they go here. Does everybody see that? If it's all right, I'm going to start to delete some of these images because we're not going to really need them anymore, at least for now. Yeah, I just set equals over that. Like here, let me pull it up. I just did it cell by cell and said equals that. Nothing complicated. Let me do something. There we go. All right, so you all should have something should look something about like that. You have a local stiffness matrix, a rotation matrix. We then rotate that stiffness matrix to obtain a global one, then figured out where those terms belong in the whole system. Everybody good? Now, what I'm going to do is this, okay? Because I'm lazy. Now that I've got this all figured out for an element, I'm going to copy and paste this all down here, and I'm going to do it again. Okay, so we're going to call this element number 2. Now, before I start editing any of the cells in these terms, element number 2 is associated with what degrees of freedom? What are my codes going to be? 3, 4, 5, 6, right? So let's go ahead and change that right now. Okay, so 3, 4, 5, 6. 3, 4, 5, 6. I'll just copy and paste that. I ain't got to change anything on the green matrix because that corresponds to the whole system. We know the whole system 6 by 6. Before I start doing anything over here, is anything over here valid? This isn't valid at all, is it? Like, these cells don't belong here. They're ultimately going to belong down there. So let me delete this. All right. See what I got? Okay. Now, let me show you something. There's a reason why this copying and pasting thing's kind of nice. Remember this yellow matrix? That was kind of a pain in the butt to put together, wasn't it? It was kind of a pain in the butt. Well, watch this. If I highlight that and look at my formula, look, it's already done my math for me. I don't have to type all that stuff in. What I do have to do is change the cells in these values here. I got to change that. But ultimately, I don't have to do that matrix multiplication again. So let's start doing some formatting. First off, I need to change all these to 2s. We're talking about element 2, so this is beta 2. And I have a prime here, but I actually don't need that for the beta. I just noticed that. Don't need that. This is K2. This is K2. Okay. Let's review. Let's start off at the very beginning. Local stiffness matrix. Most of it is 0 except for this, 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 and this, right? And those are AE over L, right? Do we have AE over L for element number 2? And it's, what is it? 432 something. Watch this, okay? I'm going to go into the cell, okay? Watch this. If I go into the formula bar, see this blue cell here? See how it's referring to that? I'm just going to go here and move it, like literally physically move it up there. So now I don't have to type anything. And same thing here, just move it. Move it. See how when you move your mouse cursor, it turns into the arrow and the little 4 arrows there? That's the pan button. It's basically just panning that cell over. And then panning. Excuse me. Now, are we done with this? What haven't we fixed? This is way wrong, isn't it? We're talking about that diagonal element, right? The diagonal element is not going to be ones, 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 and ones. What fit inside this cell? Sines and cosines, right? Here's my sines and cosines. I'm just going to do the same thing. Cell by cell, let's see. That's a cosine, needs to move up. That's a sine, needs to move up. Sine needs to move up. So I'm literally clicking inside the formula bar, dragging with my mouse, hitting enter. So your K matrix in global coordinates is a mess. But again, this member is diagonal, okay? Y'all see what I did? Let y'all go ahead and update that. So that'll just go up. There you go. Okay, well, you've already deleted everything. Hold on. Okay. See how this term, okay, watch. I clicked inside there and just see, watch. See my mouse? See that? Just drag it up. Press enter. See what I'm doing? Click inside here and drag it up. Oh. Drag it up. Hold on. First off, undo button. Okay? Okay, now, that, drag it up, hit enter. Go ahead, click up there. There you go. All right, so just, okay, you click inside your formula. So see how it's highlighting that right there? Okay, watch. See how I move and I get that? See that right there? Drag. Hit enter. That way, I mean, you can retype the formulas if all you want. You can retype them if you'd like, but that would just be a lot quicker. Yeah. Okay, remember, we're going off of, let me see something. Oh. Keep going back this way a little bit more. See, this is the pattern, or if you want, you can follow that right there. Yeah. Well, no. See, look, you're highlighted on that term, which is supposed to be negative sine. So you typed in 0 because it happened to be 0 for that first member. That's fine for that first member, but the reason why I was so rigorous last time is because we'd be repeating this. Okay. Now some of you have already gone ahead, and that's fine. Those terms are going to populate right here, aren't they? In this lower right coordinate, because 3, 4, 5, 6, 3, 4, 5, 6. So they belong right here. So I'm just going to grab here and say equals that. Do that. Everybody see that? So what do I do if I'm assembling and I have overlapping terms? I add them together. So this is the assembled stiffness matrix for element number 1 right here. This is for element number 2. If I want it for the whole thing, maybe just put that there. I just say equals that plus that. And take that cell, fill the whole thing. So that's the K matrix for the whole system. What's your check? Okay. Values along the main diagonal. 241, 0, 587, 86, 345, 86. What characteristic do all those values along the main diagonal possess? They are positive. What else? The transpose and the original matrix must be identical. In other words, it is symmetric. Here's entry 3, 1. Here's entry 1, 3. 1, 3. See that? They're identical. Let's pick one. 5, 2 is 0. 2, 5 is 0. 6, 3, negative 172.9. 3, 6, negative 172.9. Does everybody see that? That's your indication that what we have done is correct. Is everybody okay with this? Now, what I would suggest is that this is the part of the problem that was different, largely. This was the different part of the problem, was the fact that we had to go through and do this matrix multiplication before assembly. We didn't have to do that last time. But all in all, in my opinion, this problem is the same as what we did before, other than this. Okay? So now that we've gotten through this, do you all feel comfortable with these additional steps? Okay. Now, let's again walk through what happens next so that you all understand. We're not going to go into this today. I just want you to understand. What do I do from here? What do I do to this matrix? Strike out rows and columns, right? To get this central core right here. Okay? What do I then do? I have a force vector, 0 minus 10, get my displacements. Take my displacements, split them apart. Y'all see where I'm getting this? I'm getting this right here. Okay? Plug and chug, get your displacements, split it apart. Look, it's coming right off here. Is everybody okay with understanding how we translated the information on this into what we did here? Y'all think you can continue? All right. Then let's talk about this problem. I'm actually going to give you all a little bit of time on this, okay? I'm going to give you till next Thursday, okay? So I'm going to give you a little bit of time on it. But I want to walk through it with you, okay? So this, I haven't uploaded it to MU Online yet. I will, okay? So I have given you a plain truss shown, and I'm going to have you all do some analysis. Now, how many members did we have in that example we did together? 2? How many members are in this problem? 4, 5. There we go, 5. So it's not harder, it's just longer. Okay? So for every member you have the same A and the same E, but you have different lengths, obviously. Okay? Pop quiz, what's the length of this member? There we go, 120 inches. There we go. Consistent units. Okay? Here's the member code, or the series of degree of freedom codes that we're going to use for assembly, so make sure you're following that when you do the assembly for this problem. Again, you might have assembly values all over the place. You all found that out on the last homework, so I'm sure you'll find that out on this one. What I want the displacements at each of the joints. I want the forces in each of the truss members. I want the support reactions. So make sure you're eliminating the appropriate rows and columns. Everybody good? Okay. That's all we got for today. Here's what I would like to see. What we're going to do on Thursday is I'm going to come in. You know, If I were you, I would at least try and go through the example that we did in class and try and finish that out, even if it's just rough. Finish it out. Now, you have the solution to that example, right? So you should be able to replicate all those values pretty easily. I mean, it's not like, you need to come to me and say, well, what's that displacement supposed to be? It's right there. So at least for your own edification, you should continue with this example and finish it. On Thursday, if you want, at the very beginning of class, we can go back to this example, and if you all have any questions, we can go through it, make sure we're all good, and what have you, and then carry on and move forward into beams, okay? But for now, I'd like to end it because I don't want to, put too much material into the lecture. But what I will say is this, just to give you a taste of things to come, the complicated portion with trusses was the fact that the members were oriented all sorts of different ways, so that led into the need for coordinate transformation. For beams, we don't have to deal with that because beams are just like that. They're all flat. What's complicated with beams is the fact that the loads are not applied directly at the joints. I have a beam, uniformly distributed load. How do I handle that? That becomes complicated real quick if you don't have fixed-end force tables, which we do, and we'll talk about how we can use those for beams next time. Everybody good? All right. I will see you all on Thursday. Well, hold on.